Okay, so we're going to finish up with a little bit, the last bit of topology, and then we're going to talk about some elementary functions in elementary complex functions. This is often how it's done. You introduce some of the basic functions, and they sort of illustrate some of the differences between the real value versions and the complex value versions, even in the simplest case. We're going to do it in a sort of dissatisfying way. We're going to introduce the functions in a sort of dissatisfying way, but that dissatisfaction will be resolved, will be remedied later on. Okay, and I'll explain what I mean by that soon. Okay, so finishing up the topology stuff. Basically the last two or three things. One is this thing called the distance lemma. If you have a K and F subsets of C, and the intersection of K with F is open. So you have disjoint sets. One's called K, one's called C. If one is compact and the other is closed, then actually there exists some positive number rho such that z minus w is greater than rho for all z in K and all w in F. So there exists an actual positive distance between the sets. That's what this is saying. Right? If one set is closed and one set is compact, so one set is closed. Let's call this kind of closed one. This kind of compact one. One set is closed and one set is compact. Then there exists a definite distance, a definite positive distance between things. It can't be the case that there will be points that are arbitrarily close in the two sets. There's a distance between them. Okay. So here's the idea. So the idea, maybe I can draw it first. So here's our compact set. Here's our closed set. The exterior is open, right? FC is open, right? And so each point in K can be covered by some point some ball that's interior to F of C, right? F complement. F complement is open, and so each of these guys can be covered by an open set, right? An open ball that's contained in there. Right? So you cover each of the points in here can be covered by some open ball. Okay. And then you cover you cover the whole thing you cover all of K with these open balls. You can take a finite subcover, and then you use that finite subcover to create your row. Okay, so use that finite subcover to create your row. Let me write it out. K is an LC, which is open. So for each C and K, there exists some radius R of Z, right? So that the ball of radius RZ, centered at Z, is contained in FC. Okay, so that's just what we were just saying. Right? For each point, here's F. We know that there's some, if we call this thing Z, there's some radius RZ, so that the ball doesn't intersect F. Okay. Okay. So then what we do is we cover K with all these balls, but we'll shrink the radius by half. Okay. So we take instead of taking the full thing, we'll take half the radius. Okay. cover K with all these guys. Right? And K is compact. So there's this finite subcover. There's this finite subcover. B1 half R Ci, I goes from 1 to n. Right, so there we can choose, there are endpoints. Right, there are endpoints we can choose. So that their half radii cover the whole thing. Okay. And what we do is we let rho then equal the smallest of these half radii. Everyone all right? Okay, so right, the full R doesn't intersect F, and instead we take the half radii and cover the thing with the half radii, and then we use the compactness to take a finite subcover. Okay, and then we take the smallest of the half radii as our rho. Okay, so now why is it true? Can somebody tell me why? Why, if for any z and k, is the distance from z to f always going to be bigger than this, like bigger than that rho? That half radii is what we're,
none of the balls intersect F, because F comes interior, and you just made all the balls small.
Exactly. Yeah. So suppose let's pretend that there's often it's a useful trick just to think there's only one point, or let's just pretend that there's only one ball in the subcover. Okay, it'll be clear to see that, right? You say, okay, here's my F. Suppose that we have only one ball, right? Then if you pick any point in K, it's going to lie in this ball because there's only one ball, right? It lies in this ball, and how close could this point be to F? Well, at the very worst, right, it's going to be here, right? It's going to be here. But even if it's there, its distance to F is more than half this length here, right? Which is rho. Right? Rho is half. What rho would be half this distance? And then, z being inside the half ball means that z's distance to F is greater than half the radius, right? Maybe it's too small. Right here, right here is the half. So here is z1. Here is rz1, right? And here is F. Right. Here's K. Whoops. K is here. Right. This is Z1. If we pick some point Z in here, well, how close could it be to F? Well, at the worst, it's going to be half the radius to F. But rho is half the radius, and so we're farther than rho away. Yeah.
Why do you have to cover K with these half radii?
Yeah.
Like, if we already said that the full radius doesn't intersect the set F.
Yeah, well, it doesn't intersect it, but that wouldn't give us the control over, that wouldn't give us a control over how close we can get. Right?
so
Because
that's right.
right, because we could still, this thing could still, these full balls could still be pretty close to F. Right? Right, but we want to establish a lower bound to that. We want to establish that, that these points are greater than a certain distance away, and greater than some non-zero distance. Okay, so that's why we need it. Okay, so you say, well, look. So once you choose your row, so you choose your row as the minimum of those guys, and you say, well, okay, then for any z in K, I'm sorry, let me use P, because that's what I'm using in my notes. P, it must lie in one of the B 1/2 R Z I naught, right? It must lie in one of these things in the cover, right? Okay, and so the distance from P to Z I naught is less than 1/2 R Z I naught. Right? So it lies here Z I naught, and we know that the distance from P to Z I naught is less than half the full radius that we got at the beginning, right? And so, but the distance from Z I naught to F is greater than R Z I naught, right? So the distance from P to F is greater than 1/2 R Z I naught, which is greater than equal to rho, right? Because rho was the minimum of all these half radii. Yeah.
So I see why the argument doesn't work if you only have K's closed but not compact. Because you can't get the finite, so you can't take the minimum. But intuitively, when I'm imagining like two closed disks, I can't imagine them not having some distance. Like intuitively, it seems like them both being.
Now, don't forget that closed and bounded means compact,
Okay.
right? So if you're imagining two closed and bounded sets, then you're actually dealing with you're actually stuck with compact sets.
Okay. So is there
So you have to use an unbounded set in your example. You have to use a closed. You have to take this one to be closed and unbounded. To create a counterexample, if this one had to be closed, you'd have two closed sets, but one of them will have to be unbounded, right? So for example, right, you could have something like this, right? Right. This is your K, this is your K, and this is your F. Right. And there's no minimum distance between these two guys, although they never intersect. Oh, John?
Yeah, because on if you're not in C, you're on a different metric space, does this proof work then? Since you don't necessarily have closed and bounded?
So this doesn't depend on the Heine-Brill theorem, right? This is just a statement about compact sets and closed sets.
Well, where you say you can cover the set with balls of 1/2, or doesn't that depend on it kind of?
I mean, you're in a metric space, but if you have a metric space, then you can.
And you can always cover a space of balls of any size you choose.
So being open simply means that in a metric, being open in a metric space means that every point is contained in a ball, right? Contained in a set, right? So it may not be your Euclidean ball, but you'll have some notion of ball in your metric space. Yeah. Alex.
Okay, so if those sets are getting arbitrarily close to 0, wouldn't, like, in some sense that line be a limit point? I don't know if this is like a function, if these are two sort of parts of this. You know what I'm saying? But wouldn't, like, that line in the middle be a limit point if there isn't some distance between them, and then if they're close?
You can't say that a line is a limit point. Right?
Well, okay. Well, I'm not sure what you do. That's what I'm saying.
No, but so this is just this is the axis here in the middle.
So are these functions?
So we're on the complex plane, say we're on the complex plane, and you have you look at you could say this is like you take something like the function of 1 over x, okay, and then negative the function 1 over x, and look at those two sets there. Make it a solid boundary. Okay. Then those two sets are closed, right? Yeah. Those two sets are closed, and they become arbitrarily close to each other. And they become arbitrarily close to each other.
Well, they're right, but they're coming arbitrarily close around that axis, right? So doesn't that mean those points along the axis are limit points?
No. Right, for each point, right, and this happens no matter how far I go out, I can draw a little circle around it. Okay. Yeah. So no. Okay. Other questions? Okay. Okay. Last big idea. Uniform continuity. Uniform continuity. Okay. So we have some function from B to C, and you have suppose you have the following property. Say f has the property that is such that given any epsilon greater than 0, exists delta greater than 0, such that f of w minus f of c is smaller than epsilon whenever w minus z is less than delta. Okay. For all, such that for all w minus z, f of c minus f of w is less than epsilon whenever w minus c is less than epsilon. Okay. In that case, we call f uniformly continuous. Uniformly continuous. Okay. So it's something stronger than continuity. It's saying that but I'm going to draw this on the real line. So let's pretend that you can talk about uniform continuity for real functions just as you can for complex functions. On the real line, what this is saying is that given any epsilon, you can find a delta. So somebody gives you an epsilon over here. Okay. Somebody gives you an epsilon over here, and it turns out that you can find a delta so that whenever you have any pair of points that are delta apart, their outputs are going to be less than epsilon apart. Any delta who are less than delta apart, their outputs are guaranteed to be less than epsilon apart. And that works for any pair of points everywhere. Okay, so it's not just at one point. Certainly if you're continuous, right? If your function is continuous at some point, you could say, oh yeah, I can find some neighborhood, some delta neighborhood here, so that as long as people are within delta of x naught, the outputs are going to be within epsilon of f of x naught. Right? That's continuity. But this is something better than that, right? It's saying that not just for one point, but for every pair of points in the domain, every pair of points in the domain that are less than delta apart, the outputs are going to be less than epsilon apart. So the continuity is uniform throughout the domain. Okay? The continuity is uniform throughout the domain. If not the case, so for example, if you look at you look at 1 over x, say, you'd say, is that uniformly continuous? If I give you an epsilon and I say, can you find me a delta so that whenever you have, I'm going to take my epsilon, here it is. Can you find me a delta so that whenever two guys are delta apart, their outputs are always smaller than epsilon apart? No, right? Maybe you can over here. Maybe you can over here, right? You say, oh yeah, it looks to me that if I take my delta to be something like this, yeah, as long as points are this far apart, the outputs don't vary that much. But over here, when I get closer to here, I could have 2 points that are quite close together, but their outputs vary a lot. So the continuity isn't uniform. Okay, isn't uniform. Okay, and turns out that you can get around, you can guarantee uniform continuity by requiring compactness of the domain. Okay, so a function from k to c, k is compact, and f is continuous. Okay, then f is actually uniformly continuous. Okay. The proof of this is kind of cool, I think. Oops, when I'm writing definition, it should be theorem. Continuous on a complex set guarantees uniform continuity. So somebody gives you an f. Somebody gives you an epsilon. I see as I grow older and older that I was wrong to mock my previous teachers for always making careless mistakes. There was one teacher at the University of Chicago, who would say things like, "Suppose you have a manifold M," and like, what? and we all ridiculed him at the time, but I see I'm heading in that direction. Like, somebody gives you an F, and I write epsilon. Sorry, professor. I'm not going to mention your name on the air. But the joke about that professor, there were various jokes about that professor, including, he was sort of legendary as a bad professor, as a bad teacher. One of the jokes though was that he only used 2 symbols in his classes, alpha and gamma, but the alpha was rotated counterclockwise 45 degrees, and the alpha was rotated clockwise 45 degrees. Okay, back to, let's see if I can manage to pull this off. Maybe that's why my heart was beating. Okay. If somebody gives you an epsilon, and you want to find the delta that works, right? You want to find the delta that guarantees everybody, so it guarantees that whenever 2 points are within delta of each other, their outputs are going to be within epsilon of each other. Right? So here is your setup, right? Okay, so you're looking for a delta, you're looking for some radius. You're looking for some radius, right? You're looking for some radius that whenever 2 guys are within that distance here, within that distance of each other here, then the outputs are going to be within epsilon. Okay. So what you have is continuity. So let's use it, right? F is continuous. Okay. So for each point in K, we know that we have continuity. Each point there exists a delta dependent on P such that f of the ball of radius delta is contained in, say, the half epsilon ball around f of P. And you'll see why we need the half epsilon in a second. Okay. So we have, you have P, you have f of P, and somebody's given you an epsilon, right? Somebody has given you an epsilon over here, and you say, I'm going to take half epsilon neighborhoods here, take half epsilon neighborhoods here, and I know by continuity at each point that there's some delta. There's some delta neighborhood of P, so that this thing gets mapped inside the half neighborhood, half epsilon neighborhood. Right. Okay, right. That's what continuity says. Right. Continuity says, given any epsilon here, we can find a neighborhood around a point, so that this neighborhood gets mapped inside that one. Okay, so we do that for every single point, and we cover each. You know what we're going to do. This is a compact set argument. Cover each point with the disk JP, which we will take as the neighborhood of P of half the delta neighborhood. Okay. So for every, we knew that there's a delta neighborhood, we're going to cover K with half delta neighborhoods. Right? We shrink all the neighborhoods and cover K with those guys. Okay. And then of course the next move is obvious. K is compact. So there exists. K is included. K is covered by some union of these disks. And as sort of as before, we choose any delta so that delta is smaller than the minimum of these half radii. And it turns out that delta is the one that will do it for us. Okay, so we claim now that delta works. Okay, so let's see it. Pick any P and Q in K, so that the distance between P and Q is less than delta. Right. Let's pick two points whose distance is less than delta, and let's see that their outputs differ by less than epsilon. P, one of them, it doesn't matter which, let's take P. P must lie in some JPK. What does that tell you? That tells you that the distance from P to PK is less than delta PK over 2. Okay. The distance from P to PK is less than delta PK over 2. That's what it means. Right. And the distance from Q to PK and the distance from Q to PK, well, the distance from Q to P is less than delta, which is less than half of delta PK over 2, and the distance from P to PK is less than delta PK over 2, so the distance from Q to PK is less than delta PK. So this is less than Q minus P plus P minus PK. less than delta plus 1/2 delta pk, which is less than delta pk. Okay. But that's the end, right? Because we knew what was this delta pk, right? Each of these things, right? The distance from p to pk is less than delta pk. The distance from q to pk is less than delta pk. Remember what delta pk was. Delta pk was chosen so that any point in there, any point of less than distance delta pk to p, lies in the epsilon over 2 neighborhood of f of p. K. Okay? F of pk. Right? So, right? So that's the end. You say, well then the distance from f of p to f of q is less than or equal to f of p minus f of pk plus f of q, f of pk minus f of q. Right? But the distance of p to pk is less than delta pk, so that means that this thing is less than epsilon over 2. The distance of q to pk is less than delta pk, so that means that this thing is less than epsilon over 2. So the whole thing is less than epsilon. Yeah. Yeah, Christian.
Would you mind going back and saying again why this 1 over x isn't uniformly continuous?
Yeah. But actually, let me get to that in a second, and I'll stick with this for just another moment more. So, does anyone have questions about this? Right. Remember what we did? We said let's cover each point with a neighborhood, so that anybody in the neighborhood, any point in the neighborhood, will have an output lying in the epsilon over 2 neighborhood. Epsilon over 2 neighborhood of fp. Okay. And then we covered k with those guys. We took a subcover, we took a finite subcover, right? And then we took delta to be, we shrunk those guys, and then covered it, took finite subcover, and took delta to be the smallest radius of all those balls. And then we say, okay, let's see that delta actually does it for us. And we see, well, we take 2 points whose distance is less than delta from each other. Well then, it turns out that by how we've constructed it, if these two guys are less than delta from each other, then their distance from some point is going to be less than delta pk. There's going to be some pk in there, so that each of their distances from pk is less than delta pk. Okay. What does that mean? That f of p minus f of pk is controlled by epsilon over 2. F of q minus f of pk is less than epsilon over 2. And so by the triangle inequality, right, here we use the triangle inequality, f of p, the distance from f of p to f of q must be less than epsilon. Okay, so we use the triangle inequality. As usual, we try to control something with something that we have no control over. We introduce some other factor. We break it up into things that we can control. Right? So we have this f of p minus f of q. Can't really do much with it, but we've constructed it in such a way that each of these points is close to pk. So we throw in the pk. Right? We say this f of p minus f of q is the same thing as this minus pk plus pk plus f of pk. Right? We throw in this our fancy looking 0 as always. Right? And then we use the triangle inequality to say that this is less than or equal to this thing plus that thing. And we can control each of these things. So that's the analyst's strategy always. Take your problem and break it up into other problems, into smaller problems, each of which you can deal with. Break your problem into smaller problems, which are manageable. And this doesn't work in reality, I'm afraid. When you're arguing with like actual human beings or your spouse, break your problem into smaller problems. It's not, as a pedagogical tool, like you can't teach your children this. Break your problem into smaller. I'm trying this actually, with my 7-year-old daughter. Okay. Yeah, it doesn't work yet. Okay, questions?
I have a secondary question on this actually.
Yes.
So right before this line that you have that begins with the imply symbol, so like
Here.
yeah. So right before that line, are you trying to show that P and Q are in the same JPK?
They are. P lies in a JPK.
Mm-hmm.
Q actually doesn't lie in the JPK, but it lies in the bigger ball. In the delta in the unshrunken, non-shrunken. It lies in the double of JPK.
Oh, okay.
Okay, but that's still okay because that doubled guy would corresponded to the half epsilon ball.
Mm. Yeah.
Okay. Yeah. Okay, so back here, to see that this thing is not uniformly continuous, you'd say, well, look, can you find me a delta so that any 2 points within delta of each other in 0, infinity? So, can you find me a delta so that any 2 points are guaranteed to be within epsilon of each other? And the trouble is that you can find one that works. You can find one that works out here as long as you chop off this guy at some point, it'll work.
Mm-hmm.
Right? If you start from here and go onwards, right, it'll work. But the thing is that as you get close to here, you can find points that are very close to each other, and yet the jump between them is as big as you want.
Right. Okay.
Right, because this is one of them. Right. So it's not uniformly continuous. It's continuous, but the speed is too fast.
Okay.
Right, the slope becomes too fast. So so you could say, if your function, the slope of your function is bounded, well then it's going to be uniformly continuous. And if you have a Lipschitz function, it's going to be uniformly continuous. But okay. What time is it? Is that clock 1 hour off, or is it just 1 hour?
3:30, 3:27.
Thank you. Okay. Okay. So there's this last thing in the section called the path covering lemma, which is a consequence of the two previous results. I'm just going to state it. Let E be open. And let gamma from A to B and E be a path. If gamma is continuous, then there exists a delta greater than 0 and a subdivision A equals T naught, T1, T2, blah, 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 Tn equals B, such that when the ball of radius rho around gamma rho T is contained in the set for all K. So here's your picture. You have some path that's lying inside something like this. What it's saying is that it's possible to get a row and a subdivision of the path so that each of these balls centered at each of these points is a radius rho, and something like this occur. I'm just gonna draw it. Okay, so what's gonna happen is that you take all these things are balls of radius, the same radius rho. There's going to be some fixed radius rho, so that if we take balls of radius rho around each, and there will be points, so that if we take balls of radius rho around each of these points, you're always going to contain the next point and the preceding point, if there is one. Okay, so you're always going to contain. Let's see. Gamma t is contained in the ball of radius rho around gamma tk for all t in tk minus 1, tk plus 1. For the inside guys, for k being 1 to n minus 1. Okay. So it will the ball is going to contain the path. It's going to contain the next point and the previous point and the path between. Okay. It will contain the next point and so if this guy is t gamma tk, the ball around it, a radius rho, is going to contain gamma tk plus 1 and gamma tk minus 1, and it's also going to contain the entire path between those 2 points. Okay, and the same thing happens for every point in the middle, and at the endpoints, of course, there's no path before or path after here, and so you just rewrite it to compensate for that. So there's, you describe what happens at the endpoints as well. But basically, this is what happens. So this is the path covering lemma. It seems sort of a strange thing to put down, but we're going to need it. We're going to need it later when we talk about something called analytic continuation of functions. Yeah, John.
So I can't quite read that. If gamma is what? It implies that there's this.
If gamma is continuous.
Oh, okay.
Yeah. Sorry. CTS. Okay. Okay, so that's the path covering lemma, and it's a consequence of the previous two results. Okay. So there's actually one more thing in this section. That's called the Riemann sphere. Can somebody tell me about the Riemann sphere? Who knows about the Riemann sphere? What do we mean by the Riemann sphere? Yeah.
This is hazy, but I know
that's all right. I'm probably going to say almost the same thing.
It's just like a unit sphere
yeah.
where it's centered all over 0,
okay.
And then every point in the complex plane you can imagine as a projection onto the
yeah. So basically, what you do is you identify every point in the complex plane with a point on a sphere. Okay, so you basically consider the sphere to be the complex numbers. It's the sphere of complex numbers. So there are a couple ways of doing it. You take the complex plane, okay, and one way is, as Christian just said, at the origin you take a unit sphere and put it on top. Okay, you put a unit sphere on top. I'm going to do it a little bit different. It doesn't matter, but. Instead of putting it on top, I'm going to sink it halfway through the plane. Okay, so I have this plane. I have this sphere that is here is this thing here is the unit circle on C, right? And there's this sphere that's half above and half below the plane. Okay. And what we're going to do is introduce a projection from the sphere to the plane, or you could think of it backwards, you're going from the plane to the sphere. Anyway, there's an identification of points on the sphere with points on the plane. Okay? And that identification is called stereographic projection. Okay. And so you could think of this as one way of creating a map, some sort of taking whatever's on the sphere and projecting it onto a plane. Right? It's one way of creating a map. Okay. And so the way you do it is like this: you take the North Pole, and for every point on the sphere, you draw a ray from the North Pole that passes through that point on the sphere, and see where it hits the complex plane. Okay. And then you identify those 2 points. So you say, I'm going to consider these 2 things to be basically the same thing. Okay. So yeah, okay. So in this way, you create. Do everyone see that? Right? You take a ray from the North Pole, and for any point on the sphere, you pass a ray through that point and see where it hits the plane, and that's going to be your projection. Okay. Or vice versa, right? For any point on the plane, you see where you draw a ray back to here and see where it hits the sphere, and that's going to be okay, that you consider those things to be you create a map. You create a map given by this. Okay. Okay. So yeah, there's not too much I want to say. As you get farther and farther out in the plane, what happens to your points? Where do the points go?
Close to n.
They get closer and closer to n, right? Farther and farther out, you get closer to n. If you are inside, if you're in the unit disk, then where do you end up? You're going to end up in the southern hemisphere, right? If you're outside of the unit disk, you're going to end up in the northern hemisphere, right? And the farther and farther away you get from, right? The farther and farther, the larger numbers you get, the higher up you get here. Okay. So what you get is one obtains, in fact, a one-to-one continuous. It's in fact continuous in both directions. So, it's actually now from from the sphere, excluding the North Pole, to the complex plane. Okay. Those of you who have seen topology before, this continuous in both directions is called a homeomorphism. Yeah, so these things are homeomorphic to each other, in case you know this term. If you don't, it doesn't matter. Okay. And what one does, it's sometimes convenient to add n to the sphere, to complete the sphere. And in fact, to compactify it. Okay, because you add it, and then you get this compact set. When denoting it by infinity. Okay. And one calls this set of C union the North Pole the extended complex numbers, extended complex plane. Okay. Right. As your values as the moduli of your values gets greater and greater, your your numbers get closer and closer to the North Pole. And so it makes sense to call this North Pole infinity. And so, for example, if I say something like this, z bigger than some huge number. If I'm looking at a disk, the exterior, I take a huge disk out here. Okay, I take a huge disk out here and I look at its exterior. What does that correspond to on the sphere? What does that correspond to on the sphere?
Antarctica?
Yeah. Yeah. It'll correspond to a circle, right? A circular cap, right, around the North Pole. Antarctica. Right? The polar cap, right, around the pole, right? And so this sort of thing is called a neighborhood of infinity for obvious reasons, right? This you consider to be a ball around infinity, just like you've got balls around, right? You have balls around other points here. Okay. Other things that can be shown. What happens to a straight line? If you take all the points on the straight line and you project them onto the sphere, what happens?
Comes like an arc on the
Philip?
like a semicircle. Yeah, like an arc on the side.
Well, what's going to happen? Let's think. So you're going to end up with, it'll become an arc, but right, keep on going. Where is the arc going to meet up with itself? The North Pole, right? It's going to end up meeting up with itself in the North Pole. And what you get is actually a circle. You get a circle passing through the North Pole. Okay. So this map actually has some nice properties. So maybe I'll just, I'm not going to. So in fact, we're not going to prove it, but every circle on the sphere maps to a circle on the plane, circle or line on the plane. To, and vice versa, of course. And to any two curves on the sphere intersect at the same angle when mapped to the plane. That's to say, this is what's called a conformal map. We'll see more of conformal maps later, but this map preserves angles. Again, we'll see more of this later. Okay, so now let's go on. We're going backwards now to section 1.3, elementary complex functions. We're going to do this in a really, mathematically, it's going to be very unsatisfying. So, but just bear with it. It's no matter how unsatisfying it is to you, it is at least doubly so to me. So just understand that I'm equally frustrated, or even more so than you are. Okay. So here's what we're going to do. Don't throw anything at me. Throw it at the author. We define. I'd like to throw something at the author, but I don't actually. We define for y in R. E to the iy as cosine y plus I sine y. Okay. this is actually not the way you'd want to do it, but we're going to do it anyway. Okay. And then later on, so so the real way to do this is like this. Later, in chapter 3, I think, we'll see that one can extend the definition of e to the x to complex numbers. That's what you want to do. Right? You want to define e to the x for complex z, right? How are you going to do it? We're going to do something we did something very strange here. It's not satisfying. What we would like to do, what we will do later, is do it in the following way. What we'll do is by proving that the power series summation x to the n factorial converges for all z and c. Okay. So we'll talk about convergence of series of complex numbers, and then say okay, and then we can use this to extend the definition of e to the x to the whole complex plane, okay, in a good manner. And then we'll do the same thing and do similar things for cosine and sine. Cosine and sine, and then what we'll see is that this actually holds to be true once you make those definitions. Okay, that's the actual way to do it. But for now, just as a shortcut to give you some functions to deal with, because you don't have any functions yet, we're going to just say let's define it. Let's define e to the iy this way. Okay. And similarly, again, we define for z equals x plus iy, e to the z as e to the x times e to the iy. Okay. Again, with the same comment. This isn't really how you would do it, but we're just going to use this as a sort of, it will turn out to be true later anyway, and so we're going to use it as a shortcut now to give you a bunch of functions, to introduce a bunch of functions. Even though this is not a definition, but rather a result. Right? This is in reality, this isn't how you define it. This is something that turns out to be true. Once you create the functions. Okay. Now a bunch of observations. So now some observations, all of which are pretty trivial. So let z equals x plus iy. Number one, the modulus of e to the z is, of course, the modulus of e to the x cosine y plus sine y. Right, but that's just e to the x, right? Because the size of cosine y sine y is 1. Number two, the argument of e to the z is, of course, y, right? The argument is y. So we also want to throw in all those other valid arguments, 2 pi n, where n is in z. Right? So the arguments of e to the z are all y plus integral multiples of 2 pi. Number three, trivial observation, e to the z equals 1 if and only if z is equal to 2n pi I for some n in z. That's as obvious as I think it is. Number 4, e to the z, this function is periodic, 2 pi I periodic. Because e to the z plus 2 pi I is going to be e to the x cosine y plus 2 pi plus I sine y plus 2 pi. Right? Which is, of course, e to the x cosine y plus I sine y. Right? Which is e to the z. So it's a periodic function, right? It's a function that has a period. The period is this imaginary number, yeah, right? As you move, right? If this width is 2 pi, this width is 2 pi. You take some point z, and you look at z plus 2 pi. Then e to these values are going to be the same value. Okay, so it repeats itself, right? It repeats on each strip. Okay. We can take any strip. You can take any strip and slide it over, and you're going to get the same function again. Okay. Any questions so far? Okay. Number 5. For z prime equals x prime plus I1 prime, e to the z plus z prime actually does turn out to equal to e to the z times z prime. That actually has to be shown. Using our definitions. Okay. The way you do it is not right. So you'd say, you get e to the x plus x prime cosine y plus y prime plus I sine y plus y prime. Right. And then you'd use trigonometric identities. In fact, you get e to the x plus x prime, then cosine y plus I sine y, cosine y prime plus I sine y prime from the addition formulas for the cosine and the sine, and that will give you this. So the exponential function actually does behave as you would like it to. Okay. Couple of remarks. And so, I'm sorry, it's just a bunch of simple observations. Notice that 1 and 2 imply that one can, given any w in C, excluding 0, one can find z in C so that e to the z equals w. Right? Because look, these two things here describe e to the z completely, right? They tell you what its modulus is, and they tell you what its argument is, right? And so if somebody gives you a point and says, can you give me something can you give me a z so that e to the z is this w? All you need to do is choose just choose z so that z equals x plus iy, so that e to the x is the modulus of w, right? And y is the argument of w, is one of the arguments of w, right? And you can, of course, right, just take x to be the natural log of the modulus of w. Where this natural log, just to make a point, this natural log is not what we're going to define in a second. This is your old-fashioned real natural log, not the complex natural log that we'll deal with in a second. Okay. So what do you see? What you see is that the exponential function, right? The exponential function maps the complex plane onto the complex plane minus the origin. Right? We just said, given any w, we can hit that w. Right? So this map is onto. Right? You have an onto map from here to there. Okay. In fact, it's much more than onto. It's remember what we said. The thing is 2 pi I periodic, right? So whatever the image is, that whole image is going to occur in a strip of height 2 pi, right? So in each strip, it actually maps each of these strips onto the complex plane minus the origin, right? And it does it again, and it does it again, and it does it again, and it does it again. So infinitely many times, it maps onto the complex plane minus the origin. Okay. So in fact, any horizontal strip of height 2 pi is mapped onto the complex plane minus the origin. Okay. And then the notation in the text that they use is they let a y naught be the x plus iy in C, where y is bigger than or equal to y naught and less than y naught plus 2 pi. Oops. So it's the half open strip that starts from height y naught and goes up to height y naught plus 2 pi, but not including the upper boundary. Okay. So any horizontal strip like this, and any of these guys is mapped onto the plane, excluding the origin. Okay. In fact, for each y naught and r, e to z is a 1-to-1 map from a y naught onto c minus the origin. Okay. So if we restrict the exponential map to any one of these strips, it's actually a 1-to-1 map from there to the plane. And the proof involves this fact. The only thing we need to show is that it's 1-to-1. So say that z1 and z2 are in one of these strips, and suppose that say that e to the z1 equals e to the z2. In that case, e to the z1 minus z2 is equal to 1, using what we just proved. And so, so what does that tell us? That tells us that z1 minus z2 must be some integral multiple of 2 pi I. Because the thing that I just erased said that the only things that get sent to 1 are integral multiples of 2 pi I. Okay, so this thing gets sent to 1, and so it must lie in the kernel. Right? It must be some multiple of 2 pi I. Okay, but z1 and z2 both lie in the same strip, right? So they can't differ by more. They can't. The integral multiple of 2 pi I must be 0. Right, because they lie in a strip of height 2 pi I. Right, so z1 minus z2 must be 0 2 pi i's. Right, and so z1 equals z2. And so any 2 points in that strip that get mapped to the same point must be the same point. Okay, so each point gets mapped to a unique point in the plane, and the exponential function maps any half-open strip of type 2 pi onto the complex plane minus the origin. So next time we'll talk about the inverse function, the logarithm, right? Well, the inverse function will have to be. We're going to have to talk about the exponential function is infinite to 1, right? So we have to restrict the domain to talk about the inverse function, or alternatively, what we can say is that our inverse function will be a multiple value function, where every point in the complex plane minus the origin will correspond back to an infinite number of points, each of which differ by 2 pi I. All of which differ by multiples of 2 pi I. Okay, and so we'll introduce so-called multiple value functions, which are something new for complex numbers. Okay, that's it for today.